We want to verify that the function satisfies the conditions of the mean value theorem on the interval -3 to 3, and we want to find values of c such that the conclusion of the mean value theorem is satisfied. So again, we have to take a close look at this function because we'll notice that we have this thing under a square root. And we know that anything under a square root has to be greater than or equal to 0. No negatives under square roots. If we add x squared to both sides and flip this thing around, we get that x squared has to be less than or equal to 9. And that means that x has to be between -3 and 3, including the endpoints. Now, the mean value theorem requires that our function be continuous on the closed interval, and it is just barely. But how about the derivative of this function? Is this function differentiable? Well, we think of the square root as a 1/2 power, and when we take a derivative, we get this. We reduce the power to -1/2. And don't forget that the chain rule says you have to multiply by the derivative of 9 minus x squared, which is -2x. Now, a bit of simplification means we cancel our 2's. In the numerator, we're left with a -x, and this whole term can come to the denominator, and we get that as our derivative. Now, you'll notice that we still have the same term underneath a square root. So we might think that our domain of our derivative here is all x values between -3 and 3. However, this square root is now in the denominator, meaning it can't equal 0. And this term will equal 0 when x is 3 or -3. So we have to remove 3 and -3 from the interval. Fortunately, the mean value theorem only requires that our function be differentiable on the open interval given. So this is an open interval. So this is actually okay. This is just barely okay. It barely satisfies the conditions of the mean value theorem. Our function is continuous on the closed interval -3 to 3 and differentiable on the open interval -3 to 3. Now let's start looking at the conclusion of the mean value theorem. In this problem, our a is -3 and our b is 3. And if we plug either 3 or -3 into our original function here, you'll notice that we just get 0. So the slope of the secant line between the two endpoints of our interval happens to just be 0. What the mean value theorem then says is that there exists some c on that interval, -3 to 3, such that the slope of the tangent line, or the first derivative evaluated at that point, is also 0. Well, let's see. We found a first derivative of this function, didn't we? Let's plug c into that first derivative. Okay, so there's some value of c for which this statement is true here. And we could do this algebra a couple different ways. One way would be to say, well, we can multiply both sides of the equation by this denominator here. That would just give us c equals 0, or -c equals 0. The other argument that we can make is that this left-hand side can only be 0 when the numerator is 0. And the numerator is 0 when c equals 0. So either way, we get that the value of c, guaranteed by the mean value theorem, is 0. And the only thing that we need to consider is that c on the interval that was given? Yes, it is in between -3 and 3. So we did it.